Dear Endless Astra addicts, open your eyes and ears for this one, because a Harvard University professor found out that 49 light-years from Earth, a planet is losing part of its atmosphere, and that loss is how astronomers discovered the atmosphere was there. High above LHS 1140b, helium atoms are being heated, lifted outward, and carried into space. As the planet crosses in front of its star, those escaping atoms absorb a tiny fraction of the starlight. The signal is faint. The planet itself cannot be photographed in surface detail, but the helium left a fingerprint. And that fingerprint has given astronomers the first clear evidence that a rocky world inside another star's habitable zone can retain an atmosphere for billions of years. This is not evidence of alien life. It is not oxygen. It is not a photographed ocean. But before scientists can search an exoplanet for water, climate, or biological chemistry, they must answer a more basic question. Is there any atmosphere to investigate at all? For LHS 1140b, the answer is now yes. But that opens a stranger question. How did this planet keep its atmosphere while orbiting a type of star known for stripping atmospheres away? In September 2024, LHS 1140b passed directly between its star and Earth. Astronomers observed the transit with a Weinard spectrograph on the Magellan Clay Telescope in Chile. They were not trying to photograph the planet. They were separating its star's light into precise wavelengths. During a transit, most of the planet blocks the star, but a narrow portion of starlight passes through the outer edge of the atmosphere before reaching Earth. Atoms and molecules absorb particular wavelengths, leaving signatures in the light. Near 10,833 angstroms, the researchers found the signature of metastable helium. The absorption appeared during the transit. It also seemed to begin before the planet fully crossed the star, suggesting that some helium extended ahead of the world along its orbit. There may also have been a weaker trail behind it. The upper atmosphere was not perfectly still. It was escaping. Astronomers know the atmosphere exists because they caught part of it leaving. Before we go deeper, subscribe to Endless Astra for more real cosmic stories built on science, not fiction. The story became more complicated in 2025. During another transit, astronomers did not recover the same helium signal. That does not automatically erase the 2024 result. Independent analysis recovered the earlier detection, and researchers examined other possible causes, including Earth's atmosphere and activity on the star. A more interesting possibility is that the escape changes over time. The amount of high-energy radiation reaching the planet may vary. The upper atmosphere may heat and cool. Stellar wind may reshape the escaping gas. So the atmosphere can remain present even when the helium fingerprint is not always equally strong. The planet has an atmosphere, but that atmosphere is dynamic. LHS 1140b lies about 49 light-years away in the direction of Cetus. Astronomically, that is nearby. Humanly, it is almost unreachable. The light entering our telescopes today began its journey roughly 49 years ago. Even a message traveling at light speed would need another 49 years to reach the system. The planet orbits a small, cool red dwarf called LHS 1140. It completes a full orbit every 24.7 Earth days. That sounds extremely close to its star, but the star is far dimmer than the Sun. LHS 1140b receives only about 42% of the energy Earth receives from sunlight, placing it inside the star's habitable zone. The planet is approximately 1.73 times Earth's radius and about 5.6 times Earth's mass. Yet habitable zone does not mean inhabited. It does not guarantee oceans. It does not even guarantee a habitable surface. It means only that the planet receives an amount of energy that could allow liquid water under the right conditions, the right atmosphere, the right pressure, the right chemistry, the right climate. A world can orbit at the perfect distance and still be an airless, irradiated desert. That is why the helium detection matters. It confirms the condition that makes every other question worth asking. But red dwarfs create another problem. They are the most common stars in the Milky Way, and their small size makes their planets easier to detect. When a planet crosses a small star, it blocks a larger fraction of the star's light, producing a stronger transit signal. Because red dwarfs are dim, planets can also orbit close to them and still receive temperate levels of energy. That makes these systems excellent places to search. But young red dwarfs can be violent. They may release ultraviolet radiation, X-rays, flares, and charged particles. A nearby planet can have its upper atmosphere heated again and again. Light gases rise. The atmosphere expands. Some of it escapes. Over billions of years, the star may strip a world nearly bare. This created a major uncertainty in the search for habitable planets. Rocky worlds around red dwarfs may be common, but can their atmospheres survive? LHS 1140b now shows that under at least some conditions, the answer is yes. It has lost material, but it was not completely destroyed. The planet's large mass may help. With more than 5 times Earth's mass, it has stronger gravity than a smaller rocky world. Its star also appears old and relatively quiet compared with many red dwarfs. It still produces enough high-energy radiation to drive escape, but it is not among the most violent stars of its class. Gravity, atmospheric chemistry, and the star's long-term behavior may have allowed enough gas to remain. But helium reveals only the uppermost part of that atmosphere. The lower atmosphere is still hidden. It could contain nitrogen. It could contain carbon dioxide. It could contain water vapor. Or it could contain a mixture unlike anything around Earth. James Webb Space Telescope observations have already removed one major possibility. LHS 1140b does not appear to have the large, lightweight hydrogen atmosphere expected around a miniature Neptune. That kind of atmosphere should have produced strong molecular features, and those features were not found. The remaining possibilities include an airless world or a denser atmosphere made from heavier gases. One analysis found tentative evidence consistent with a nitrogen-rich atmosphere. Tentative is the important word. It is possible, not confirmed. The helium result may fit a world whose lighter gases escaped more easily, while heavier elements remained lower down. So escaping helium could be tracing only the thin outer boundary of a much denser environment beneath it. Astronomers now know gas surrounds the planet. They still do not know what most of that gas is. And the planet may contain another major ingredient. LHS 1140b is less dense than a completely dry world made only of rock and iron. Models suggest that a significant fraction of its mass could be water. But a water-rich planet does not automatically have a global ocean. Its water could be frozen at the surface. It could exist beneath an ice shell. It could be compressed into high-pressure ice deep inside. Or it could be divided between frozen and liquid regions, depending on the atmosphere and climate. Then there is the most dramatic possibility. LHS 1140b may be tidally locked, with one hemisphere permanently facing its star, and the other trapped in endless night. Under certain conditions, atmospheric circulation could move heat away from the dayside, while a circular region facing the star remains warm enough for liquid water. From orbit, the planet might resemble a dark pupil surrounded by ice, an eyeball world. It is a fascinating model. It is not an observation. No telescope has photographed an ocean there. No continent has been seen. No surface cloud has been mapped. Every image of the planet's landscape is an artistic reconstruction based on mass, radius, orbit, temperature, and climate models. The real discovery is much smaller in appearance. It is a tiny dip in a spectrum. But scientifically, that faint line is worth more than a beautiful fictional ocean. Because it is measured. Now that an atmosphere has been established, astronomers can ask better questions. How thick is it? What gases dominate below the helium? How quickly is it escaping? Can it move heat between the day and night sides? Could water remain liquid anywhere? Nitrogen would matter because it can provide surface pressure. Carbon dioxide would reveal more about the greenhouse effect. Water vapor could strengthen the case for accessible water, although it would not prove an ocean. Eventually, astronomers may search for combinations of gases that should not remain together without continuous replenishment. That is the basis of biosignature science. Not one molecule, not oxygen alone, not an announcement of alien life. A possible biosignature must be interpreted alongside geology, climate, stellar radiation, and time. LHS 1140b is not yet at that stage. The helium detection does not prove habitability. It makes habitability testable. And there is one more remarkable part of this discovery. The atmosphere was not found by a spacecraft visiting the planet. No probe entered orbit. No camera photographed its surface. The evidence came from a telescope in the Chilean mountains. Light crossed nearly 49 light-years of space, entered an instrument on Earth, and revealed a change caused by helium atoms around a world too distant to resolve directly. The planet appears only as a temporary reduction in starlight. The atmosphere appears as an even smaller change hidden inside that reduction. And yet the signal was enough. For most of human history, planets beyond the solar system were only possibilities. Then, astronomers began finding them, first by the dozens, then by the hundreds, then by the thousands. Next came small rocky worlds, then planets inside habitable zones. Now, one of those worlds has revealed an atmosphere. LHS 1140b may eventually prove frozen, hostile, and lifeless. It may hide water beneath ice, or it may become one of the first places where astronomers seriously investigate the climate and chemistry of a temperate rocky world beyond our solar system. Whatever the answer, the first barrier has been crossed. Scientists spent years asking whether a rocky planet in another star's habitable zone could keep an atmosphere through billions of years of stellar radiation. Now, they know that at least one did. 49 light-years away, helium is escaping from a world we cannot see clearly. And beneath that escaping gas may be the next major clue in humanity's search for another living planet. Drop a comment. What should astronomers search for next on LHS 1140b? Nitrogen, carbon dioxide, water vapor, or a genuine chemical biosignature?